I showed you some titration curves. These ones on the left, actually, I showed you before, for a weak acid with a strong base. But the calculations for a weak base with a strong acid, which is done in the case of like amine bases, the calculations are exactly the same, except you have to think in terms of starting with a base, right? So you're going to have a base plus water, plus sodium hydroxide in your titration. Sorry, base plus a strong acid like HCl in your titration reaction. And we'll do one example of these later, but because they're exactly the same and they do take a lot of time to do, we're just going to do like one at midpoint or something, and then we'll go ahead and do that as an example. But notice how these curve shapes. This is like reverse world, right? It's like flipped upside down, and so this is the shape that you would get for a weak base. Now we've talked a little bit about equivalence point pH, and in the equivalence point pH for all weak acids, right, they're going to be above 7. That's this point here. Oh, let me just put a dot on here. There's your equivalence point. For a weak acid with a strong base, it'll always be above 7. The only time it's ever 7 is when it's a strong acid, strong base. We also talked about the pH at midpoint being equal to the pKa value for the acid. And so this one's 5.9, midpoint's about 12.5, so that's actually this value in here, right? And then we also talked about the equivalence point volume being exactly the same for the strong acid and strong base, regardless of strength. It's all based on molarity or moles, really. It's all based on moles. Now, when you look at a weak base being titrated with a strong acid, right, and these were the same concentrations of volumes of weak acid and weak base at the start, you notice the titration volume is exactly the same. Again, it's just based on moles and not what the substance is. And so the other thing, though, that's interesting is if you take this weak base and you calculate its pKa, it turns out it's 8.5, right? 12.5 milliliters, this is 8.5. So in fact, what we said here for weak acids where pH at the midpoint of the titration is equal to pKa, it's actually true for bases as well, right? But you start with a Kb and you calculate the pKa, and that tells you what this pH will be. If you notice at pH 7, right, this is pH 7 is right about here. The pH at the equivalence point is below 7 for the titration of weak bases. So like I said, it's like reverse world, right? Like if it's below 7 for an acid at midpoint, then it's above 7 for a base. And if the equivalence point pH for a weak acid is above 7, I think I just said that wrong. Yeah, well, if the equivalence point pH is above 7 for a weak acid, for a weak base, it's below 7. I think when I was talking about midpoint, I think I might have said equivalence point a couple of times, but kind of lost track. And also the pH at the end, right, of the titration is determined entirely by the excess strong base for a weak acid titration, and it's determined by the excess strong acid for a weak base titration. And so that's why these things, because these molarities of titrant are the same, they look like opposites of each other, like reverse world, okay? So having said that, let's look at a couple other titration curve trends. Now remember I said the equivalence point can be predicted based on midpoint pH, that's this, and where the titration ends. It doesn't really matter once you're past this point here. You could take a value along this curve and average it with this point here, and that's almost always right on the equivalence. It's almost always right on this equivalence point pH. So while you can do calculations sometimes in the lab when you're just trying to get an idea of what indicator to use, because those are pH sensitive, we can just average the pKa with, let's say, 12 or 13, and that usually tells us a good range for the indicator. Okay, so here's a set of sample data similar to the one I gave you for the strong acid, strong base, but this is now a weak base with strong acid, and it's 25 mils of base, so that's in your Erlenmeyer flask, and it's being titrated with 0.1 molar HCl. Now, since these calculations are so similar but just a little bit different, and they do take a lot of time, I'm only going to show you the one example here, and we'll calculate a pH on the titration curve. And I think it might be useful to calculate the pH at midpoint. So midpoint is half of the equivalence point, and so this is 25 for the equivalence point. There we go, 25 equivalence point right here, right? And so, and it also shows it over here, so I'm not really guessing that much. What we're going to do is we're going to calculate the pH, let's say right here, halfway, so at 12.5 milliliters. So our volume is like V of titrant. That's going to be 12.5 milliliters. And that's what we need to do this calculation. And we're also going to need to have a KB value, and I'll give you that when we get to the calculation. Okay, so we need an ice table, and we need moles of acid and base, right? So I'm going to go, the titration reaction is the base plus HCl, and that's going to give me HB plus, now B is this, right? That's my base, plus Cl minus from the hydrochloric acid, the leftover, right? And this is going to be my mice table. So I have moles, right? This is millimoles. So I have initial, my change, and then I'll say E, but it's not really equilibrium, but it does make the mice work, and it's kind of cute, so I'm just going to do it. I had this argument for years with one of my colleagues that it shouldn't be an E, but then it's just so darn cute to call it a mice table that it's just couldn't help myself. Anyways, yeah, sorry. So we need to know moles of the base, so it's these two multiplied together. Oh no, sorry. Sorry, these two multiplied together. I can keep track where my eyes were. That's 2.5. Yeah, millimoles. And then for the HCl, it's these two multiplied together, right? So that's 1.25 millimoles. So, and my total volume is 37.5 milliliters. So I got all the numbers I need for my calculation. So we can roll on it now. So we're going to say this is minus 1.25. That's my limiting, right? So minus 1.25, and this is going to be plus 1.25. You can still do x's if you want it. I just think it looks cleaner just to put the 1.25s in there. So this is going to be 1.25, and this is always true at midpoint. You've burned up half your acid or your base at midpoint. This will go to 0, and now this will be 1.25. Now, again, this calculation, except for the reaction at the top, is exactly the same as the weak acid. And now we're going to do the equilibrium calculation. And this really is an ice table. It has to have molarities and such. So I'm going to write my reaction first. So I have HB plus oh sorry, my bad, B plus H2O in equilibrium, right, with HB plus OH minus. That's the hydrolysis reaction. I always got to remember, it doesn't like me drawing at the bottom. I should have just made another slide. Sorry. We'll just sort of work through it. So this is my I, C, and this is E, right? And so I actually need to know molarities. So I'm going to take and calculate my molarity as 1.25 millimoles divided by 37.5 milliliters. and that's going to be 0.033, like that, something like that. And it repeats, so I'm just going to do that to save a little space. And you'll notice that this is 1.25 and this is 1.25, so this calculation actually applies to both. So I have 0.033 repeating, and then I have 0.033 repeating here, and we'll assume that that's 0. And again, the water we don't care about. This will be minus x plus x. I'm sorry, golly, it's getting late actually. Plus x, like this. So I'll have 0.033 minus x and 0.033 plus x and x. And so KB, because this is a KB reaction, right, it's going to be 0.033 plus x times x divided by 0.033 minus x. And these 3's are repeating. So when I do the calculation, I'll go ahead and plug those in. Now, this KB value, the one I've used before, is 1.8 times 10 to the minus fifth. And I know that looks just like the one for acetic acid, or very similar. Just a coincidence, but it's the one we use all the time. So now I can solve it for x. So that's 1.798 times 10 times 10 to the minus 6. I don't know if I had that pause while I did some of that, but anyways, that's what x comes out to be. And so now I can calculate from that value my pOH, and then I'll calculate my pH. Sorry, I looked at it again. I didn't have scientific notation on. This is actually 10 to the minus fifth, okay? So as a pH, pOH is negative log of this value. So I'll write it up here because I'm running out of space. pOH is 4.75, which means pH is 14 minus that value. Pop my calculator up. So I actually didn't do the negative sign, so I have to add 14, but there we go. 9.25. So this comes out to 9.25, like that. All right, so that's the midpoint pH, and we can go to 12.5 right here. Now, let me get the laser pointer up. Maybe I can't get the laser pointer up. It's being on. There we go. 12.5 milliliters, and go up to here, and that should be about 9.25. The other thing we can do is go over here at 12.5, and you notice it's somewhere in between these two values here, so it's pretty close. All right, so it's almost exactly the same calculation that you would do for a weak acid. It's just that you have to be careful about which equations you're using, and keep track of the idea that you're generating hydroxides, so you're getting pOH instead of pH. But in all other aspects, it's very similar to the weak acid calculation.